Optimal health for high performers. This is the Health Upgrade Podcast with Dr. Nawaz Habib.
Hello, everybody. Welcome back to the Health Upgrade Podcast. This is Dr. Habib. I'm here with JP. How are you, sir?
I'm doing really well. Thank you.
Wonderful, wonderful. You just gave me a bit of a rundown and something that I think we'll be able to share a little bit about during this episode, that you had a great little checkup, and there's some really interesting developments in terms of how your health has benefited from a lot of these lifestyle things that you're adding in. But we want to talk today about mitochondria, but in the context of how can we support them from other cells, and the fact that the mitochondria are not stagnant within a single cell for our entire lives. And sometimes there can be some support that's provided from other cells in potentially transferring or transplanting mitochondria from one cell to another. And this is an emerging science, something that is very interesting. We're seeing and we're hearing a lot more about it really in this longevity space. And we're really interested in kind of digging into how does this build to a point of supporting our health for long-term health optimization, for health span, for longevity. Okay. Why don't we start off talking about cardiovascular system and the role of the mitochondria there? And I just want to quickly, before we jump in there, say that I was listening to the Huberman Lab podcast with Dr. Martin Picard, which, by the way, in my opinion, one of the best conversations I've ever heard with these two gentlemen speaking to one another. And Dr. Martin Picard is a mitochondrial specialist, is what he's, and researcher. And his research is, and his perspective was so unique and so powerful in being able to connect kind of Eastern wisdom and the flow of energy into a Western medicine front, and talk about how the mitochondria are these very important energy transfer mechanisms. They're the tools that allow for the flow of energy to occur, the conversion of the form of energy. And that, I think, was a really unique perspective. And the conversation was just really, really amazing. So I wanted to bring that up because he talked about a really important piece in there, that there are different types of mitochondria in different organs. These are called mitotypes. And these mitochondria have the same genetic structure. They still have the maternal DNA within their mitochondria, but this maternal DNA is also played along with cellular differentiation. The mitochondria differentiate in that way as well. And so in our heart, we have different types of mitochondria than we do in our brain, than we do in our lungs, than we do in our liver, because the form and the frequency of ATP production need to be different in the heart than they do in the liver, for example. And so there's different mitotypes based on the cells that they're within. And I just thought that was a really unique perspective. So let's talk a little bit about mitochondria of the heart, because that's really where a lot of this emerging science of mitochondrial transfer is being identified. So I'll pass it on to you to dig into the cardiovascular side.
So remember that while mitochondria do carry their own DNA, that DNA over the 1.5 billion years that mitochondria have merged into eukaryotic cells, that mitochondria has been pared down dramatically. The mitochondrial DNA is only a few, not even a few, a couple of dozen genes. And most of the mitochondrial proteins that are required for mitochondria to exist are actually genes in the nuclear DNA. There's really only a few that remain in the mitochondrial DNA. And you're absolutely right that it is in part so that mitochondria can specialize in the specific cell type that they're in, or the specific mitochondria itself. But any nuclear DNA is subject to epigenetic control. And that's what happens when cells differentiate. When you have a stem cell that's progressively differentiating down to be a muscle cell or a skin cell or a brain cell, a neuron, it's changing which proteins are going to be expressed in that cell. And that includes the mitochondrial proteins. So, maybe not to the same extent that, a skin cell differs from a liver cell, but still you see a difference, difference in biogenesis potential, difference in ATP production, et cetera. So, specifically looking at different types of cells, you see something like a skin cell that, may not have very many mitochondria in it because they're really not doing that much. They're serving as a barrier, so they have some things that they need to produce and energy needs. But compared with a neuron, or probably the most energy intensive cell in the body, if not a neuron, is going to be a cardiomyocyte. That's the muscle cell inside your heart. It's got to be on. It's got to be on for, if you want to live to 90 years old, it's going to be functioning for 90 years. Maybe not that specific one, but, by and large, we don't make a lot of cardiomyocytes. You lose those, not a lot of regenerative capacity. If you've damaged your heart muscle, it doesn't repair the same way if you, damage your calf muscle. So you got to be careful about that. But you made a reference to my own medical situation, so I might as well just dive into it because it's really got me jazzed about this topic to talk about mitochondrial health, mitochondrial transplant, mitochondrial transfer. And I think it gives us a chance to maybe revisit some of the therapies that people are being told to use for cardiovascular disease. So basically, most of cardiovascular disease centers on or is the consequence of occlusions that form in the blood vessels, what we call atherosclerosis, the formation of an atheroma inside the blood vessel that narrows it, and it can be unstable, it can rupture, and you can have thrombotic events, which is clotting, which can be catastrophic, both in terms of strokes or heart attacks. But all of that process, when we think of atherosclerosis and the clotting or buildup of lesions inside your blood vessels, the first kind of class of drugs that come along that people think about are, well, you got to take a statin. That's a cholesterol problem, or you got to be on a, if you're sort of cutting edge, you're thinking, oh, bempedoic acid, or maybe a PCSK9 drug. And all of those are focused on cholesterol and specifically on low density lipoproteins, or LDLs. And, you have to sort of go back and say, is that really what we're fixing? Is that really where the problem is? And so my own personal story is probably pretty fair to share. I mean, I'm going to give you some numbers of my own blood work in the process, but, I'm 57 years old. And since my, at least my mid-20s, I have had pretty high cholesterol. I mean, or what people in medicine would consider high. And my LDLs were also pretty high. So it was fairly common for me to have a cholesterol level north of 220, 240, and LDL levels that were, 140, 150. And, sure, I had physicians say, you need to go on a statin. And I said, I don't really think I do. I think I'm fine. And this is in the face of having two grandfathers, both of whom had heart attacks. So, you think to yourself, why would I steer clear of a drug like a statin, which millions of people take, if I have a family history of heart disease? And I said, no, I just don't think that I need to do that because I am a runner. I am getting out there and running every day. And I didn't really, fully understand it when I was in my 20s or even in my 30s. But as I sort of continued on, I decided that I was going to stick to my guns, stick to what I believed was the true science. And I wasn't going to take a statin. I was going to continue to exercise. I wasn't going to cut down on red meat. In fact, over the last, several years, I've become probably an even more stringent carnivore. Probably have a steak every night. Actually do have a steak every night. And I just wanted to see, how things were going. So, 8 years ago, I went in for, one of those executive physicals, spent a few $1,000s, had them do elaborate blood work, do a stress test, do the CT angiogram. And sure enough, cholesterol level came back, I think around 240. And yet my CT angiogram, which is an elaborate visualization of your cardiovascular system, showed zero plaque anywhere. My calcium score was 0 and I had no plaques. That was 8 years ago. I was still in my 40s. And so I decided, I hadn't done one in a while. I decided to go back and get some blood work done. And the blood work came back with even higher cholesterol levels. And I did it right. I fasted from 8 o'clock the night before. They didn't draw the blood until practically noon the next day. Hadn't eaten anything because I'm an intermittent faster anyway, so I wouldn't have. But they collected blood and they gave me back the results. Cholesterol level 292, LDL 190. Now my HDL was 89, which is also very high. And I started thinking about it. I'm like, all right, I believe in what I've been talking about. I believe in what I preached, but nothing proves it better than getting some evidence and visualizing it. So I signed up to do a CT angiogram, and sure enough, went in and still 0 calcium, 0 plaques, both calcified plaques or soft plaques, 0. So across the board, cardiovascular health, exactly where I would have expected it to be and hoped it would be, despite these elevated levels. And so that got me thinking, maybe we need to share with people what it is that's actually going on in your cardiovascular system and why it's not an LDL problem. It's not a cholesterol problem. As I say, if your body is making cholesterol, which is really where your circulating cholesterol levels come from, it's not from what you eat, it's from your liver. If people are worried about that, then they're worried about the wrong thing, because that's not what, once you understand how that cascade works, you're going to see that LDL is just a bystander. It's not the issue. So let's start again with what the structure of a blood vessel looks like. Okay. We're talking about an artery, and on the inner layer, there's an endothelial cell or endothelial cells that provide a robust but thin barrier so that nothing can get from the bloodstream through that barrier unless it's specifically needed, unless there's a specific transporter or some mechanism for allowing that to get through through the layer. But even before you get to that endothelial layer, there's something called the glycocalyx. And I don't think a lot of people, maybe some of the people listening to this podcast will know what a glycocalyx is, but I suspect most don't. Glycocalyx is a thin layer of basically sugar-like molecules. It's almost like a fuzzy interference layer,
Hence
if you will.
glyco. That's why it's called glyco.
Yeah, glyco. Exactly. And that glycocalyx sits as sort of a armor, if you will, on the endothelial cell. So as blood flows by, the actual interface isn't blood cells or the contents of the plasma with the cell itself. It's with this glycocalyx. And over time, if that blood flow is laminar, which means that it's smooth, there's no turbulence in that flow or shear, then the glycocalyx remains healthy, and it keeps that barrier with high integrity. But in areas where there's shear, where there's either oscillation in the flow or shear builds up, it starts to wear away that glycocalyx. Now, the glycocalyx is being built from the inside out. So, or I should say, from the inside of the endothelial cells outward. So the glycocalyx is constantly being built up, and some of it is being worn off. It's like sandpaper. Your blood flow is going to come by and it's going to knock things off. But if it's laminar, if it's smooth flow, you don't get that break off. Inside the endothelial cell is where the problems start to arise. It's not in the blood supply. It's in the endothelium itself. When the endothelial cells start to become, let's say, dysfunctional, and they become dysfunctional when the mitochondria start to fail, when the mitochondria start to produce reactive oxygen species and other problems occur, then the endothelial cells stop making the glycocalyx, and the reactive oxygen species are actually like acid on that glycocalyx, and it starts to break down. You end up like literally with like a cheese grater layer. thinned glycocalyx with holes in it. When that happens, now the shear forces of cells going by, et cetera, are triggering the endothelial cell to change how it functions. It's being triggered to have a response that's maladaptive. Yes, there's a reason why endothelial cells would do those things that it's about to do, but not under these circumstances. So there's a failure mode that's happening. And what happens is the endothelial cell starts to stop producing nitric oxide, and it starts to allow through the layer LDL and other materials that are lipids, and it allows in through by literally putting on its own surface. So the endothelial cell is now expressing on its surface molecules like VCAM and ICAM and other things like that that grab onto the monocytes that are flowing. So these are immune cells that are flowing through the blood supply. All of a sudden, they become sticky. They stick to that endothelial cell, and they move into that what's called the intima of the blood vessel. So again, healthy blood vessel has a glycocalyx layer and an endothelial layer that's serving as a relatively firm barrier to anything entering. But once the glycocalyx breaks down, and it really breaks down from the inside of the endothelial cell out because of mitochondrial dysfunction, you end up with LDL flowing into the tissue, into that blood vessel wall, and what follows is mitochondria. Is macrophages and monocytes. And when they get there, they're activated. They start producing all sorts of inflammatory cytokines. They start the reactive oxygen species that were already there are oxidizing that LDL, turning that nice, fatty acid tail of that LDL into something that's more like a free radical. And so when the macrophage tries to eat that LDL, so that's where the LDL is, and the LDL is sort of passively just sitting there, it's been oxidized. The macrophage grabs onto it, eats it, can't break it down. And that makes that macrophage turn into a foam cell. Foam cells are at the heart of what's causing that growth in a lesion. So you can see how this process is progressing. It's all because of a failure of your mitochondria. It's the mitochondrial dysfunction that's taking place.
So what you're getting to here, and I think just to summarize what you've stated, is that LDL is a bystander that if it happens to be high in combination with mitochondrial dysfunction and the intima layer breaking down, the glycocalyx being broken down because the mitochondria are dysfunctional and producing a lot of reactive oxygen species to begin with, then the LDL buildup and the influx of these macrophages will lead to foam cells and calcification and plaques that will become more problematic and enable a turbulent flow within these blood vessels, leading to more shear forces, leading to more breakdown, leading to blood vessels becoming dysfunctional. And that's where, when the plaque breaks off or plugs up the blood vessel, we're then going to have this effect of a heart attack or a stroke or whatnot, right? The blood vessel diseases that happen accordingly. So LDL is not the cause. And I think that is the ultimate take home on this, that the root cause of this issue is actually mitochondrial dysfunction. And it's so common and so frequent that it's cardiovascular disease that's the most common cause or the most common disease state of mitochondrial dysfunction in the first place. Does that sound?
Exactly.
Yeah.
Exactly. What we're talking about is a metabolic problem. That's why we call it metabolic syndrome, because when you have hypertension, which is an insulin problem, essential hypertension is an insulin problem. When you have diabetes, when you have obesity, when you have this problem of a sedentary lifestyle and you're not getting, and your diet is wrong, you're not eating the right foods, you end up with mitochondria that are stressed. It's oxidative stress. They're creating reactive oxygen species. And you end up with this cascade of damage that leads to this lesion forming, initially a fatty streak, and then it's this buildup of an immune response, an inflammatory response inside the vessel wall. And the presence of the LDL is really only a function of the fact that the glycocalyx and the endothelial cell failed. It's not LDL in and of itself didn't come along and knock on the door and say, hey, I want in, and break in and cause a problem. No, the LDL is a passive bystander. It just so happens to be part of the process. Now, is lowering your LDL going to save you from a plaque that's already built? Not at all. No. In fact, if you go and you look at the studies of things like statins, even high dose statins, 40 milligrams of rosuvastatin or 80 milligrams of atorvastatin, Lipitor, you see over a 5-year period, you'll see 0.5% to 1% reduction in plaque volume. You're not going to change and that's even soft. You may calcify that plaque more readily, but you're certainly not reducing the volume of that plaque. That plaque is you're stuck with. PCSK9s, there was a big hope that was going to have a better reduction in plaque size. Nope, not at all. Maybe over a 3-year span, 2% reduction in plaque volume. And I think all of that change in volume is really a function of the fact that it is slowing down the growth of those, because there's just less LDL to be captured, but you're not, the slowing of the growth is probably lowering the inflammatory nature of that lesion. And as a result, it's the volume change isn't really a change in necrotic tissue or apoptotic cell remnants, et cetera. It's really just a function of the fact that there's less quote unquote inflammation, swelling that's taking place in that
less
area.
of an activated immune response. Yeah.
Right. So the question is, what might we be able to do in order to actually reduce the size of these plaques? Now, once they're calcified, it's probably too late. You probably can't do anything to reduce it. But what about the soft lesions, which are technically more dangerous? But what about reducing soft plaque? Could we actually reduce the size of soft plaque? And the answer is, in animal models, the answer is yes. But again, let's go back to the process that's taking place here. You got to fix the mitochondria. Now, this is why there's simply no better way to preserve or restore your health at any age. There's no better way than exercise. Exercise is and restoring or gaining cardiorespiratory fitness. We've talked about VO2 max. I'm a big believer that VO2 max and cardiorespiratory fitness are protections against really anything, whether it's neurocognitive, whether it's cardiovascular, whether it's metabolic. I mean, that there's just nothing better for you than to have that kind of exercise and that restoration of mitochondrial flexibility. It reduces reactive oxygen species, reduces inflammatory cytokine production. It restores immune function. So that's why
it allows
the
maintenance of nitric oxide production and blood
Absolutely.
flow, and why it happens so acutely, why the cardiovascular diseases where these challenges happen most acutely is because the cardiovascular disease is constantly functioning. We cannot function without blood vessels contracting and dilating, without the heart beating, without the pumping of all of these functions. And so when acutely that situation occurs, and the frequency with which these situations occur has increased over the last 50, 70, 80 years, having to do with, it's not because of the fats, it's not because of it. Take a look at the dietary trends in the world over the last 50 to 100 years. The trends are heavily towards refined and processed carbohydrates. That's really where we have to look at the root cause, and let's correlate that down to what does that cause? The answer is mitochondrial dysfunction without fail.
And it's also, it's the use of industrial and seed oils that are actually more damaging than because and not simply because of the types of molecules that are in them, but because of their
It's
inflammatory.
the oxidative nature of these things.
Yeah, they're more easily oxidized. They're more easily, they're more easily activating the damage in your mitochondria. So what the long way around is, I think that the next wave of cardiovascular medications or supplements or other treatments are going to go to this issue of, how do we fix the mitochondria? How do we prevent the mitochondria from becoming dysfunctional and leading to the breakdown of the glycocalyx, the cheese grater protection that ends up allowing in the LDL, creates the reactive oxygen species to oxidize it, and the formation of foam cells, and the ultimately the creation of this necrotic core, which is the core of this lesion that's building inside the vessel. And the answer is, there's supplements that are really good for mitochondrial health, but there's also mechanisms, and this is this mitochondrial transfer part, where if you have a really healthy immune system, your macrophages literally will trade out bad mitochondria from cells and replace them with good mitochondria. And there's multiple ways that your cells do this. We're going to dig into that, I think, a little
this
bit.
is exactly where I was excited to go with this conversation, is when somebody does make a decision and begin to change their lifestyle, when they start to include less refined foods, go towards a more whole food style diet, whether they're going carnivore or not, a less processed food diet. We know a whole foods diet is kind of that beginning point. Once they start to follow the new food pyramid, the upside down one, that is actually correct, funny enough,
which South Park figured out
years and years ago. I love it. Once we start to utilize those pieces, how exactly are we then supporting these things? When we start exercising, when we start doing cardiovascular training, VO2 max training, whatever kind of level people are getting to, when these changes start to occur, how capable are mitochondria of becoming healthy again endogenously with basic lifestyle changes? I want to dig into that first.
Very, very quickly. I mean, actually, we have the capacity in our bodies to restore our mitochondria very quickly. And we know this because if you're a sedentary person who doesn't run, doesn't do any exercise, isn't in good cardiovascular fitness, it doesn't take that long for you to get yourself back into good cardiovascular or metabolic shape. You may still be carrying around too much weight, because that just takes time to burn it off. But you will. I always tell people, if you want to lose weight, if you're carrying around 50, 60, 80 extra pounds, and there's a lot of people out there who are, okay? If you just decide you're going to go to the gym, you're going to start going to the gym, you're going to get on the treadmill and you're going to burn your fat off, you have missed the first step. And the first step is going to take you about a month or maybe 6 weeks to do. And that's the getting your mitochondria ready to start burning the fat. Because if you're a sedentary person who's not exercising and you're overweight, chances are very good that your mitochondria are not burning fat at all, that your body is relying solely on the stream of sugar either coming out of your liver or coming in through your diet. That sugar is poison in terms of trying to lose weight. You have to get the sugar levels down, the insulin levels down. You have to allow your mitochondria to become flexible, which is a process that doesn't take very long. I mean, the mitochondria are there. They have the capability of doing it. They just have to be reoriented to using up fatty acids. And you have to tell the cells in your fat cells in your body to release it. They're not going to release it if there's insulin flowing through your blood vessels or bloodstream. That's just what they do. As soon as they see that insulin, they say, "Oh, I'm going to store. I'm not releasing. I'm storing." But when we've talked about that before, but it only takes probably about 4 to 6 weeks before your mitochondria are primed and can start to burn fat.
Yeah, there's no question. That's really the most common missing piece is the rebuilding of metabolic flexibility, of rebuilding mitochondrial flexibility and changing it around, because it takes time. And I imagine during that time, and I haven't seen the research on this, but I would love to dig into this, is I'm sure there's a change that actually is occurring of either the unhealthy damaged mitochondria is being fully replaced or it's being fully repaired. So if it's capable of being repaired, I'm imagining that it takes 4 to 6 weeks for that initial repair to take place. And if it's so damaged that it's not capable, I imagine there's a bit of a transfer that can occur in certain cell types in certain areas where healthier mitochondria, more flexible mitochondria are being transplanted or transferred into these blood vessel, like the intima layer, the endothelial cells, for them to work, or for it to work in the heart, in the cardiomyocytes, or for it to work in different cells. You mentioned earlier the cardiomyocytes, and I think they're really important when it comes to specifically this mitochondrial transfer concept. Let's talk about what mitochondrial transfer is and how that process would occur.
Okay. So cardiomyocytes are, as we talked about before, a very energy intensive cell type. They are on all the time. They're keeping us alive by pumping the blood through our blood system, circulatory system. When a cardiomyocyte sitting there pumping, once a second, every day of every month of your life, they're gonna burn out mitochondria. There's just like a battery that wears out. And what we found is, and what we've seen is that the cardiomyocytes, when they have a bad mitochondria, and they've got thousands of mitochondria in them, they're filled with them, and these mitochondria are reproducing, they are fusing together, they're splitting apart depending on the needs in the specific area within the cell. And when a bad one happens, it gets spit out, and there are literally vascular or macrophages that are embedded in the tissue that take up that bad mitochondria and give back to that cardiomyocyte a new mitochondria that's healthy. Now the question is, well, what happens to that bad mitochondria? You suggested, well, maybe it gets fixed. Probably what's happening most frequently is one of two things. Either it gets degraded through a process called mitophagy, which is sort of the mitochondrial equivalent of autophagy, or it gets literally spit out into the bloodstream so that it can get filtered out by your kidneys. So the idea that we're going to tinker with the individual mitochondria, yes, that happens, and we're inside cells. That's happening all the time with new ones being created, fusing together, fissioning, splitting apart. That's happening all the time. And when they split apart, the healthier one stays, and the one that's got the damage gets either internally broken down through mitophagy or spit out. So there's a lot of dynamics going on with how mitochondria are transported. Same thing's happening in the brain. Your immune cells in your brain, your microglia cells, are literally trading mitochondria with neurons, to make certain that the neurons have enough energy to do what they're supposed to be doing. Now, in terms of the way that those mitochondria get transferred, there's probably 4 main ways. One is what are called tunneling nanotubules. So basically, one cell will just create, a structure that's a tube that connects to another cell, and the macrophage may extend this tube, and you can see parts of mitochondria flowing from one end of the tube into the other cell. In a similar capacity, there's what are called gap junctions. So between two cells, when they come close enough to one another, you can imagine something sort of bubbles out of one and then enters into the other. So there's this gap junction, this sort of very narrow, almost like a synapse, if you would think, where something can move from one cell to the other, and it's so constrained by the geometry that you don't have to worry about it leaking out. So that's another way. Another way is through, and one that I'm really fascinated by, are called extracellular vesicles, or what we're commonly referred to as exosomes. The issue with these is that mitochondria are a couple of orders of magnitude larger than the average exosome. So these extracellular vesicles that are involved in what's called, and I'll put it in air quotes, mitochondrial transfer, aren't actually carrying full mitochondria. They're carrying fragments of mitochondria, little sort of seedlings, if you will, but they're also carrying a bunch of other cargo, things like miRNAs that are associated with controlling what proteins are being made. So, promoting biogenesis, that's a term that means creating more mitochondria. Another chemical in the body of a protein is called PGC1 alpha. It's PPAR gamma coactivator 1 alpha, and that is enhancing the production of mitochondria. And that's another way that we can get a cell that receives that to promote the production of mitochondria. And I think it's really mostly a two-step process. There are stem cells like mesenchymal stem cells and hematopoietic stem cells that, under stressful circumstances where there's a recognition that more mitochondria are needed, you see them produce lots and lots of these exosomes that are promoting the production of mitochondria. So the process begins with something like a stress, like a hypoxia. Imagine going out and running. You have never run before. You're going out and running. You're going to use up oxygen so fast that you're going to actually become a little hypoxic. Okay? That hypoxia is a signal to stem cells in your bloodstream to produce exosomes that are promoting the production of new mitochondria. This is how it happens. Your body is saying, hey, I'm pretty hypoxic here from this run. I don't have enough cardiorespiratory fitness. I need to enhance my mitochondria. I need to create more. So my stem cells are going to send out these signals. That signal, that exosome, about 50 to 70% of these exosomes actually get taken up by your macrophages. So the macrophages are hearing this signal saying, hey, we need more mitochondria. Here are these exosomes. The macrophages then take them up, produce more mitochondria, and start sharing them with the cells that they're managing. It's just one more way in which macrophages, the tissue-resident macrophages, are shepherding and managing the flock of cells that they helped to build originally and are there to manage. It's a wonderful system. I mean, it's a truly amazing process that occurs, but this takes a little bit of time. And it's why I say, if you want to get to the point where you have this cardiorespiratory fitness, this resilience, this ability to be flexible, you have to go through the process of being a little hypoxic and creating more mitochondria. Now, there are some supplements that can enhance this process, so you don't have to, actually go out and get direct mitochondria infusions.
Let's dig into those.
One of them that's gotten a lot of press is urolithin A. So urolithin A is a compound that's found in pomegranates and a few other fruits. I think in some citrus fruits. It's been sold directly as urolithin A. There's some companies out there that have packaged urolithin A into their supplements that are sort of specifically for mitochondrial health. Lots of really good results. Clinical studies, randomized clinical studies showing, increase in muscle strength, increase in muscle volume, increase in cardiovascular, respiratory fitness, and by and large, just, really positive for your cognitive functions as well. So I'm a big believer in urolithin A. It's one of the few supplements that I actually do take, is a urolithin A supplement. And another is spermidine. And spermidine is found in soy and found in wheat germ and other things. And it's a supplement. It's like resveratrol, et cetera. But it seems to be a little more generic in its effects. It's not necessarily specifically enhancing mitophagy, but it does enhance all of autophagy, and mitophagy is a subset of it. And so it's a good one also.
Yeah, this is great. For a lot of people, we're looking for how do we ensure that we can optimize this function and get mitochondria functioning really well. I think urolithin A is one of the best studied of the bunch, for sure. And it's a great adjunct into this process and supporting your metabolic health, supporting your mitochondrial health, and supporting your immunometabolism, your immune metabolic function. This is where these exosomes from the stem cells that are triggered positively by good stress. Hypoxia is good stress in certain circumstances. And we need that positive benefit of stress because then we get the signals to produce the cellular functionality to manage that stress in the future and build that over time. It's the immune cells that take up these exosomes, build out these mitochondria, and then transfer them into the cells in the tissues or the organs that they're located. Immunometabolism is truly the key here, is getting the immune cells to be able to function well enough that they can produce good levels of mitochondria, internally transfer them in, and then the cells can function because they have phenomenal, well-functioning mitochondria at the end. And that's where the organs are able to do this. I love the word that you used here, that the tissue-resident macrophages are shepherding optimal function of each organ through enabling mitochondrial functionality, enabling clean, repaired, strong mitochondria to be present in each of those cells, in each of those organs. So that's truly
100%.
the key to all of this. I want to
It is.
quickly, sorry, go ahead.
And it's where your cardiovascular fitness and your cardiovascular health. I mean, cardiovascular disease is still the number one cause of death in the
By
world.
far, yeah.
And if we, and all it takes is cutting down the sugar and staying active. I mean, it's a disease. Unfortunately, it's one of those affluenza diseases. The more affluent and Western you become, the more at risk you are for cardiovascular disease.
Sadly.
So just spend a little bit of time and effort doing what it takes to keep your mitochondria healthy, and you'll stave off heart disease.
Now, very briefly, I want to quickly mention this idea of mitochondrial transplantation and the fact that there is some emerging research on literally the transplanting of mitochondria into different cells, or the full cytoplasmic mitochondrial transplantation into different cells. This is an emerging science. It's very, very new, but we've become aware of some functionality here. With very brief, your wonderful brevity, let's talk quickly about mitochondrial transplantation.
Yeah, so the two primary ways, if you want to step beyond urolithin A and spermidine and other things that are promoting biogenesis, the two strategies that are being looked at mostly are one, directly harvesting and then injecting, re-injecting, if you will, whole mitochondria into damaged tissue. So they're doing this in post-heart attack patients, post-MI, where you've got these damaged cardiomyocytes and you want to literally infuse them immediately. You don't have time to go through the biogenesis process. You want to infuse them directly with mitochondria. And that appears to be relatively effective. The question is, how long are those mitochondria going to last and how functional are they? But in a dire situation, that can be an effective mechanism. Probably the longer term solution is going to be to harvest and hold stem cells and stress them so that they produce these exosomes. As I said, the cascade of this positive cascade starts with some stress that leads to, and it might be hypoxia, leading to the stem cell producing exosomes that are filled with cargo that is promoting mitochondrial biogenesis, mitophagy, and supporting the macrophages that will ultimately be transplanting into the tissue the mitochondria that are needed. So I think we can sort of jumpstart that by injecting or infusing large quantities of these exosomes into people, and it's early days, but I'm pretty excited about the potential.
Yeah, there's a lot to be said in terms of how we're finally figuring it out, that it's the mitochondria that need to be optimized, that the source of cardiovascular disease, at the source or the root of so many of these chronic diseases that people are dealing with are mitochondrial dysfunction at the root. And so let's do everything in our power to support that, from lifestyle, exercise, dietary choices, etc. Where supplementation can be beneficial, make choices accordingly. There's no direct recommendations here. Disclaimer, you speak to your medical doctor before you make any decisions, your primary care provider, and then go out and make those decisions for how to optimize your longevity and your lifestyle. I think that's key here. Any final thoughts?
No, I think you said it really perfectly. I would find it hard to believe that if you go and consult with your medical doctor and he says, no, don't worry about your mitochondria. I mean, I would get a different doctor.
100%.
I would say if he, and it's sort of that joke, if you walk in and your doctor weighs 400 pounds and you're a runner and he's telling you your cholesterol level's too high and you need to be on a statin, I would look at him and say, you really shouldn't be a doctor.
Absolutely. All right. Well, this was a great episode. A lot of great information in here for all of our clients. If you got to this point in the podcast, share this episode with one person who you think could utilize this information to optimize their health, their longevity, and leave it to us to not talk about the vagus nerve one time, which is wonderful, directly. I'm sure it'll come back next time. We will catch you all on the next episode. Thanks for listening.